Ever wondered how fast our universe is expanding? Turns out, it's a cosmic puzzle that's keeping scientists on their toes. Imagine the universe as an ever-growing balloon, with galaxies moving away from each other as it expands. Now, scientists are scratching their heads because something doesn't quite add up in this cosmic equation. In a recent breakthrough published in the monthly notices of the Royal Astronomical Society, researchers suggest a mind-bending idea: we might be living in a giant void in space. This cosmic blank space, about 1 billion light-years wide, challenges the conventional view of the universe's structure. Picture it as an unexpected, below-average density zone, defying the norm. But hold on, this isn't just a sci-fi twist. The researchers tested their theory using an alternative concept called modified Newtonian dynamics, MOND, shaking up our understanding of gravity on a massive scale. The results? A surprisingly good match with observations, adding weight to the idea that our universe might need a gravity makeover. This revelation comes at a time when scientists are grappling with the Hubble tension, a dispute over the rate of the universe's expansion. Traditional solutions are hitting roadblocks, and this void theory offers a fresh perspective. If this holds true, it could be the nudge cosmology needs to rethink Einstein's theory of gravity, signaling a paradigm shift in our understanding of the cosmos. Part 2. The mystery of cosmic expansion. One of the biggest mysteries in cosmology is the rate at which the universe is expanding. This can be predicted using the standard model of cosmology, also known as lambda cold dark matter, cdmlambda.gsfc.nasa.gov/education/graphic history/univ. This model is based on detailed observations of the light left over from the Big Bang SOP, called cosmic microwave background, CMB. The universe's expansion makes galaxies, phys.org/tag/galaxies, move away from each other. The further away they are from us, the more quickly they move. The relationship between a galaxy's speed and distance is governed by Hubble's constant, which is about 43 miles, 70 km per second per megaparsec, a unit of length in astronomy. This means that a galaxy gains about 50,000 miles per hour for every million light-years it is away from us. But unfortunately for the standard model, this value has recently been disputed, leading to what scientists call the Hubble tension. Dewey.org/10.10/stab187. When we measure the expansion rate using nearby galaxies and supernovas, exploding stars, it is 10% larger than when we predict it based on the CMB. In our new paper, dx.dewey.org/10.93/mror/stad3357, published in the monthly notices of the Royal Astronomical Society, we present one possible explanation: that we live in a giant void in space, an area with below-average density. We show that this could inflate local measurements through outflows of matter from the void. Outflows would arise when denser regions surrounding a void pull it apart. They'd exert a bigger gravitational pull than the lower density matter inside the void. Part 3. Tweaking the laws of gravity. We wanted to test this idea further by matching many different cosmological observations by assuming that we live in a large void that grew from a small density fluctuation at early times. To do this, our model Dewey.org/10.1093/mray/staya2348 didn't incorporate CDM, but an alternative theory called modified Newtonian dynamics, MOND. MOND was originally proposed to explain anomalies in the rotation speeds of galaxies, which is what led to the suggestion of an invisible substance called dark matter. MOND instead suggests that the anomalies can be explained by Newton's law of gravity breaking down when the gravitational pull is very weak, as is the case in the outer regions of galaxies. The overall cosmic expansion history in MOND would be similar to the standard model, but structure, such as galaxy clusters, phys.org/tags/galaxy plus clusters/close parentheses, would grow faster in MOND. Our model captures what the local universe might look like in AMOND universe, and we found it would allow local measurements of the expansion rate today to fluctuate depending on our location. Part 4. A universe in flux. Recent galaxy observations have allowed a crucial new test of our model based on the velocity it predicts at different locations. This can be done by measuring something called the bulk flow, which is the average velocity of matter in a given sphere, dense or not. This varies with the radius of the sphere. With recent observations, dewey.org/10.1093/mrus/stad1984, showing it continues, dewey.org/10.93/manras/stad2764 out to a billion light years. Interestingly, the bulk flow of galaxies on this scale has quadrupled the speed expected in the standard model. It also seems to increase with the size of the region considered opposite to what the standard model predicts. The likelihood of this being consistent with the standard model is below 1 in a million. This prompted us to see what our study predicted for the bulk flow. We found it yields a quite good match. dewey.org/10.93/meanras/stad3357 to the observations. That requires that we are fairly close to the void center, and the void being most empty at its center. Our results come at a time when popular solutions to the Hubble tension are in trouble. Some believe we just need more precise measurements. Others think it can be solved by assuming the high expansion rate we measure locally is actually the correct one. dewey.org/10.146/anurev-nucal-11422-wash-euro-24107, but that requires a slight tweak to the expansion history in the early universe, so the CMB still looks right. Unfortunately, an influential review highlights 7 problems. www.mpi.com/2218-1997/9/9/393. With this approach, if the universe expanded 10% faster over the vast majority of cosmic history, it would also be about 10% younger, contradicting the ages. dx.dewey.org/10.3847/1538-4357/ACE43 of the oldest stars. The existence of a deep and extended local void in the galaxy number counts, and the fast observed bulk flows strongly suggests that structure grows faster than expected in CDM on scales of tens to hundreds of millions of light years. Interestingly, we know that the massive galaxy cluster El Gordo, hubblesite.org/content/media/images/2014/22/3361-image.homl, formed too early. physicsworld.com/a/r-gauge clusters-defying-standard-cosmology in cosmic history, and has too high a mass and collision speed to be compatible with the standard model. phys.org/tags/standard plus model. This is yet more evidence that structure forms too slowly in this model.